So today we're going to talk about MEMS gyroscopes. And this is our last topic for the course, essentially. So gyroscopes are used to measure the speed of angular rotation by sensing the magnitude of a Coriolis force that is acting on an object. So let's talk a little bit about Coriolis forces. Has anybody ever heard of a term involving Coriolis forces or anything like that before? So what have you're nodding your head north, where have you heard Coriolis used?
Like hurricanes.
What?
Aren't hurricanes made
Yeah,
by-
so like Coriolis winds and stuff like that. Absolutely right. So it has to do with the rotation of some object. Right? So Coriolis forces act Coriolis forces act on objects moving in a rotating inertial frame. So I'm going to attempt to draw something here. So this line that I have right here is my axis of rotation. And what I'm attempting to draw is a disk. So some of you may be old enough to have experienced a merry-go-round or something like that before. I don't know. I mean, they're wildly dangerous. I just assumed they weren't on playgrounds anymore. So I've got my disk here, and the black line going through the center represents my axis of rotation. Let me try to define a coordinate system here real quick. So let's say that the up direction is Z, the right direction is X, and so out of the page here would be Y like so. And let's say that our disk is spinning with some angular velocity, and I'm using capital omega here. Okay. So in a linear inertial frame, let me write this out. So that means disk not spinning. If a mass is thrown from the center of the disk towards the outer edge, the mass will arrive at some point B due to its velocity. So essentially, if I have a ball or something here, and I throw it towards the outside edge, it will eventually hit this point B on the outer edge of the disk because the ball is traveling with some particular velocity, right? In a linear reference frame, if I threw a piece of paper at Andrew, assuming my aim was true, I would probably hit him because everything is normal, right? Well, if the disk is spinning, a throw from the center directed at point B will instead arrive at a point A. And I'll put point A on a moment. Which has moved in front of the mass. So we'd see something more akin to this. So this is our starting point, and we would see, let's just call point here arbitrarily point A. And we'd see what looks to be like a curved path from the point of reference of the observer who's standing on the spinning disk. Okay. So the mass will travel a curved path from the perspective of an observer on the spinning disk. So from this perspective, the mass must have experienced a force. But to perturb its path. So this is where things get fun or interesting, because it's not really a physical force that's doing anything. It's just a force that appears like it's doing something because we're in a rotating frame of reference, right? So how many of you all hunt or target shoot or anything like that? A couple of people have gone out and fired firearms before. Okay. So depending on whether you're shooting east or west, you may have to take into account literally the rotation of the Earth to account for the fact that your target is technically spinning into or away from you, right? So you might have to aim a little high or aim a little low because the Coriolis force is going to, quote unquote, act on your projectile after it's fired from the gun because the Earth in and of itself is in a rotating frame of reference if your target is far enough away, essentially. So mathematically, this force, which is the Coriolis force, is expressed as F sub C, our Coriolis force, will be equal to -2 times our mass multiplied by capital omega where this is the angular rotation speed of our reference frame. And this will be crossed into, so that is a cross product. Let me try to draw that better. A velocity vector, v, or x dot velocity, okay? So just to be clear, that x in the middle there is a cross product, so this is a vector operation. In most MEMS devices, and we'll see why momentarily, the velocity and angular rotation axis are orthogonal, yielding the relationship where our Coriolis force FC is simply negative 2m capital omega. Actually, let me get rid of those signs. So that's just the magnitude of the rotation, rotational speed, the magnitude of velocity, and I'm going to give this a direction in the y direction. Okay. Where based on this, I'm saying essentially, so our angular rotation vector representation is in the z direction. Our x rotation or x direction is there. So our y direction should be, our cross product should be out of the page, excuse me, into the page, but that negative sign is pushing it out. But anyway, so let's look at an example here. So let's say that a micro resonator of mass m is equal to 1 microgram is vibrating at a frequency of f naught is equal to 10 kilohertz. Okay. With a vibrational amplitude of x naught is equal to 1 micron along the x-axis if the resonator is on a rotating platform with omega is equal to 2 pi radians per second, meaning just rotating once every second, with rotational axis in the z direction. What Coriolis force acts on the mass? Okay. So let's first define our displacement vector, okay? So in the frequency domain, our displacement vector x would look something like actually, let me do this a different way. Sorry, I'm going off script here, but it'll be fine. So in the time domain, because I want to show you guys who don't have an electrical engineering background where this is coming from. We would say that x of t is equal to x naught, and I'm just going to arbitrarily choose a cosine function here. So this will be cosine of omega naught t, where omega naught is just going to be 2 pi times f naught, right? So this is what our mass's oscillations or vibrations look like, okay? Well, we can choose to represent this in the frequency domain, and we tend to do this because it winds up making the math a little bit easier, okay? So let me scroll down here. So we would have x as a vector is going to wind up being x naught e to the j omega naught t in the x direction. Realistically speaking, actually, we only care about the real part of this thing, but the complex numbers, as I said, are going to wind up making the math a little bit easier. So if we substituted in numbers here, we have 1 micron, so this would look like 1 e to the j 2 pi times 10 to the 4 t microns in the x direction, where I've simply subbed in 10 to the 4 as 10 times 10 to the 3 or 10 kilohertz as my frequency. So from this, our velocity, x dot, is just dx by dt, which is going to look like j omega naught x naught e to the j omega naught t in the x direction, or j times 62.832 e to the j 2 pi times 10 to the 4t, and our units here would be in millimeters per second in the x direction. So just to be super duper clear, this guy right here is 1 micron times 2 pi times 10 to the 4 radians per second, where radians are a dimensionless quantity, and because we're going to have an answer that's well over 10,000 micrometers, that's why I'm choosing to represent it in millimeters per second, okay? So what does this j in front of our velocity represent? So in electrical engineering, we use J all the damn time, particularly when we're talking about sinusoidally excited systems, okay? And that J there usually winds up representing a 90-degree phase shift between two signals, right? So it could be the 90-degree phase shift that we see between the voltage drop across an inductor and the current flowing through an inductor as a positive 90 degrees. In a capacitor, we would see a 90-degree phase shift between the current flowing through the inductor, or excuse me, current flowing through the capacitor and the voltage drop across the capacitor, which would manifest as a negative 90-degree phase shift. So here, even though we're talking about a mechanical system, this is still representing a 90-degree phase shift. What we are seeing is that our velocity is 90 degrees out of phase with our position, which should make perfect sense when we talk about this sinusoidal vibration, right? So essentially, if I had didn't mean for this to be brown, but it'll be okay. So if this graph is my displacement as a function of time, and I'll do my displacement in red. We called it a cosine function. So it'll start here, not including any phase shift or anything like that. So on and so forth. Well, at this point right here, when my displacement is at its peak, what would my velocity be? Well, it has to be zero because essentially my oscillation is changing directions, right? So when I'm at the peak value of my sinusoidal function, my velocity has to be zero because I'm changing my displacement from increasing to decreasing, right? So that inflection point means that my velocity had to be zero. So I'm similarly, when I'm looking at this point right here, where it's transitioning through a positive displacement to a negative displacement, I'm at my fastest velocity because my displacement is changing by the largest amount. Okay, so this is literally just our velocity is just a 90-degree phase shift. It's going to look sinusoidal like this, but it is going to be shifted to the right by 90 degrees. So let me write that down. This J represents a 90-degree phase shift between displacement x and velocity x dot. Okay. Velocity is at its maximum when displacement is zero and velocity is zero. Displacement is at its maximum. All right, so putting all of this stuff together, our Coriolis force Coriolis is then FC will be negative twice mass omega velocity in the y direction, or negative J 0.790 e to the j 2 pi times 10 to the 4 t nanonewtons in the y direction, or we might write this as 0.790 cosine 2 pi times 10 to the 4 t minus 90 degrees nanonewtons AY in the time domain. So for these sinusoidal oscillations, the magnitude of our Coriolis force is simply twice m omega lowercase omega naught x naught, where, just to be clear, this capital omega is the angular rotation of the frame, or the reference frame, and this lowercase omega is the angular frequency of our vibrations, right? That's why I'm using two different omegas. Capital omega is our frame's speed, and lowercase omega is related to our vibrational frequency. Okay. So what I'm trying to show you here is that our Coriolis force that we are experiencing is proportional to our vibrational amplitude, right? This x naught term right here. So in a MEMS device, our vibrational amplitudes are going to be very small, on the order of microns. And so we need to make sure that we design our system very carefully in order to actually be able to pick those vibrational amplitudes up. So what I'm going to talk about now is so the fact that I'm multiplying by negative j is why I'm subtracting negative 90 degrees from that phase angle. Yeah, so that took care of the negative sign for me.
So the next time basically now that I can do the like suppose into the flight direction of the flight force.
Right. But if I put it in the time domain like this, so this, I don't want to get too far into the weeds of electrical circuit theory or anything like that. So this is a quick aside, and for those of you that have had me for circuits 1 or 2, take a nap for 3 minutes. Okay. So essentially, if we look on a complex number plane where this guy is 0 degrees, this guy is 90 degrees, this guy is plus or minus 180 degrees, and this guy is negative 90 degrees. If we went out 1 unit in the real direction, that's just 1, or 1 angle 0 degrees, or 1 e to the j 0 degrees, okay? If we go up 1 unit in the imaginary direction, so this is, think of this as kind of just like two number lines that are perpendicular to each other. This would be J for one angle positive 90 or one e to the j 90 degrees. If I go out one unit in the negative real direction, this is what we would commonly call -1 or one angle plus or minus 180 degrees or one e to the j 180 degrees. And lastly, run out of room, so I'll do it down here. If I go -90, that is negative j or one angle -90 degrees or one e to the minus j 90 degrees. So when I had that negative j out in front, that is the same thing as me just shifting the phase angle by minus 90 degrees. So that's why I got rid of the negative sign here and I lumped it essentially into there. I forget sometimes that not all of you guys are electrical engineers and don't have to do this constantly. So my bad. Okay, so vibrating two-mode gyroscopes. So practically all MEMS gyroscopes are an example of a vibrating two-mode gyroscope. So at a macro scale, kind of trying to explain exactly what's going on, I'm going to try to draw a picture here. So I've got essentially two fixed anchors on the left and right. And then here in the middle, I have a frame like so. So this frame, we are going to consider it to be very low mass so that we're not going to have to account for its mass later on, okay? So connecting my frame to my anchors, I have some form of mechanical suspension like so. And so I'm going to have what I'm going to call my sense vibrations in this direction. And then inside of my frame, here's my proof mass, M, and I'm going to connect my proof mass to my frame with another set of springs so that I have what are called drive vibrations in this direction. So giving myself a little coordinate system here. Here's my X direction, my Y direction, and my Z direction. And then my rotational axis is still around the Z direction in this system. So essentially what I've got is I've got a drive mode that is excited in the X direction, okay? So I am intentionally inducing vibrations in the X direction, which would be up and down in this particular page. My rotational axis is in the Z direction. So when I'm experiencing no rotation whatsoever, all I'm getting are those vibrations in the up and down direction. But as soon as this system experiences rotation, I should induce vibration left and right in the y direction. And by measuring the size of those sense vibrations, it gives me an idea of what type of angular capital omega speed I have experienced. Okay. So one of the reasons why I like gyroscopes so much, and we'll see this in a couple of minutes, is because this physically tells us what J means in a real physical system. We have two different vibrational modes that are 90 degrees out of phase with each other by definition. And we're going to find out that our response carries through that J, that 90-degree phase separation between those modes, because of how this thing is built. So it is literally a physical manifestation of what the imaginary number J means. So I love this stuff. All right, so here's a graphical representation. Now let's talk about what's going to go on here. Okay. So both the sense mode and drive mode mechanisms are composed of simple harmonic oscillators which are governed by the following relationship. So our force F will be equal to m times the second derivative of displacement. I'm just choosing to write this displacement as x generically, but obviously my y mode displacement for my sense vibrational mode and all of that kind of stuff, I would just replace everywhere I have an x with a y. So I'll have the second derivative of x with respect to time plus some damping coefficient times the first derivative of x with respect to time plus k sub x, right? So I've got force is equal to mass times acceleration plus damping coefficient times velocity plus spring constant times displacement. Just good old-fashioned F is equal to ma and all of the other different ways that we can generate a force. Okay? So what I'm going to do is I'm going to use the Laplace transform with the following conditions. My displacement at time equals 0 is 0, and my velocity at time is equal to 0 is 0. So these are just the initial conditions on my second order differential equation. And so I'm going to come out with the relationship that my force is equal to my mass times my Laplacian operator s squared times x plus my damping coefficient multiplied by my Laplacian operator s times x plus k times x. And so now I can just pull out all of those terms and I'll get ms squared plus gamma s plus k all multiplied by x. the transfer function of the system is h of s is equal to x over f and so that's going to be 1 over ms squared plus gamma s plus k. And I'm going to take that mass essentially out of that first term, leaving me with 1 over m, or 1 over my mass in my numerator, divided by s squared plus gamma over m s plus k over m. When we were talking about accelerometers, we learned that our resonant frequency can be expressed in terms of our spring constant over mass. So essentially we have the relationship omega naught was the square root of k over m. And then when we were talking about mechanical damping, we learned that our quality factor was essentially omega naught m over gamma. We wind up getting a transfer function that looks like 1 over our mass multiplied by 1 over s squared plus omega naught squared over q plus omega naught squared. Because our system is excited by steady state sinusoidal oscillations, S will simply be equal to j omega, which allows us to write our transfer function as a function of j omega. So we're going to have 1 over m multiplied by 1 over j omega quantity squared plus j omega times omega naught over q plus omega naught squared. And what we're going to do now is some complex math to manipulate this thing so that we no longer have complex numbers in our denominator. But actually, before I do that, I'm going to take this one step further. Okay. So square root of -1, or j times the square root of -1 is just going to look like -1. So where I have that j squared right there is just going to look like a minus omega squared. And so what that's going to wind up doing is I can lump my real parts and my imaginary parts together. So I will have an omega naught squared minus omega squared. So just to be clear here, omega naught is the resonant frequency of either my sense mode or my drive mode, and omega is the frequency that I'm actually exciting it at. So those could be different things. I don't have to excite it at the resonant frequency. That's what I want to be clear about. And then I'll have plus j times omega naught over q. So in order for me to get rid of having a complex number in my denominator, I'm going to wind up multiplying this guy by the complex conjugate of the denominator over the complex conjugate of the denominator. And I'll show you guys who may be less familiar with that, what that looks like here in a second. Okay. So I'm starting with just my last step. Sorry, that should not be an omega naught there. And all I'm doing here is multiplying by a particularly fancy representation of the number 1. So that would be omega naught squared minus omega squared minus j omega naught over q. And that exact same thing is going to go into the numerator. And what this is going to do is it's going to get rid of the imaginary numbers in my denominator. And it's also going to allow me to split this up into a constituent real part and a constituent imaginary part. Okay. So that's going to look like 1 over omega multiplied by omega naught squared minus, dang it, I keep putting that extra thing there, over omega naught squared minus omega squared squared plus omega naught over q squared minus j times omega naught over q over that same denominator, omega naught squared minus omega squared squared plus omega naught over q quantity squared, like so. Yes. Um, let me look back. I feel like I shouldn't have squared that, but I just want to double check here. So let me sort this out really quickly, right? So I have, let me do this in a different color. So Q is equal to omega naught m over gamma, which means 1 over Q is equal to gamma over omega naught m, right? So manipulating this really quickly, gamma would be omega naught m over q, right? So when I have this gamma right here, if I replace that with, so I'd have gamma times s would be omega naught m over q multiplied by s, which was just j omega. So I should not have had an omega naught squared there. And my m got taken care of when I took that factor of m out of everything. Okay, so thank you for that, Anna. The units wouldn't have worked out either for what it's worth, but yeah. Okay, so I have this result. And so now literally the only thing that I'm going to do is I'm going to say, since both of these were simple harmonic oscillators, I'm going to have a transfer function in my drive mode of h of d. And so that's going to look like 1 over md times omega naught d squared minus omega squared all over omega naught d squared minus omega squared squared plus omega naught d over qd squared minus j times 1 over md omega naught d over qd divided by omega naught d squared minus omega squared squared plus omega naught d over qd squared like so. And for what it's worth, I'm going to do the exact same thing for the sense mode vibrations. 1 over ms omega naught s squared minus omega squared all over omega naught s squared minus omega squared squared plus omega naught s over qs squared minus j 1 over ms omega naught s over q. Sorry, that should be an s. Omega naught s squared minus omega squared squared plus omega naught s over qs quantity squared. The last thing that I'm going to introduce to you guys for today will be, yes. Can you come point to which line you're talking about? Because there's a lot of J's.
Or the over q squared.
Mm-hmm. So from looking at this step right here, okay, I got you. So let me explain what's going on. So I have this guy right here, right? You're good with that. I literally came and plugged that exact same thing down in here. Now I'm multiplying by the complex conjugate of the denominator. So this is another one of those things where my electricals have seen me do it 1,000 times, but you guys aren't electrical, so let me explain it really quickly. So let's say that I have something real simple, okay? So 1 over A plus JB, where I've got a real part and an imaginary part, right? So this guy right here is representing the omega naught squared minus omega squared. And this B guy right here is representing the omega naught over Q, okay? So if I multiply this thing by A minus JB over A minus JB, what I'll get is A minus JB over, so I'll have A times A, which is A squared, then I'll have minus JAB, then I'll have plus JAB, and then I'll have minus J squared, B squared. Well, J squared is -1. So I have minus JAB times positive J or plus positive JAB. Those guys cancel each other out. Negative J squared is -1, so that this winds up looking like A minus JB over A squared plus B squared. Complex numbers are fun and also gross. Fun if you use them a ridiculous amount like I do, gross if you do not. So Okay, so the last thing that I wanted to introduce to you guys today are simply the displacements that we would see here, okay? So the drive and sense mode displacements will be, so our drive mode displacement x of d, so this is just, again, I'm just using the variable x as a generic thing. Whatever direction our drive mode is actually in is what you would use here. Is just going to be our drive mode transfer function times our force in the drive mode direction. Our sense mode displacement is going to be what I'm going to call epsilon q times xd plus hs times fc, where that fc is the Coriolis force, right? So our sense mode displacement has to depend on the Coriolis force, otherwise we don't have a gyroscope. So this epsilon q thing here is what is known as our quadrature error. And it is the fraction of the drive mode vibrations that are coupled to the sense mode due to manufacturing errors. So essentially, this is representing some portion of the mode conversion losses due to us not being able to perfectly establish completely orthogonal system. Okay. We'll talk about a little bit more about where quadrature error comes in and all of that kind of good stuff in our next class meeting. So this is our stopping point for today because I really need to use the restroom.